In this video, I will discuss analog to digital conversion in general, and specifically how the analog to digital conversion module on the PIC16F1719 microcontroller works. So, why do we need to convert analog signals into digital? Well, many quantities, many different signals in the world around us are analog by their very nature. Sound is an analog quantity, so as sound waves are vibrating through our atmosphere and we can hear them vibrating against our ear, we hear the sounds coming out of speakers. Those are naturally analog, and we oftentimes will want to process those things using a computer. So we need to convert those analog signals into digital so that we can process them, and in the case of digital music files, store them for later recall. We also have various sensors that detect real-world quantities, things like pressure, things like force, things like temperature, and all of those quantities are analog. You also may have dials that can turn to any particular position, and that is analog by nature. Rather than having set fixed points, which could be digital, you have maybe a potentiometer or something that outputs an analog quantity, and we need to be able to process how far those dials have been turned. And so in order to process this analog data with any kind of a digital device, we need to convert from analog into a digital representation. And so the problem is that these digital systems are natively digital, these analog quantities are natively analog, and so we need a system that can figure out how to represent those things in the digital world. So in order for that to happen, we go through an analog to digital conversion. And what this will require is for us to sample changing signals over time at a set interval in order to get a better idea of what that overall signal looks like. So here is an example of sampling an analog signal and converting it into a digital representation. As you see here, this thick black line represents an analog signal that is continuously varying over time. Our voltage on the vertical axis, time on the horizontal axis, and these different points represent the snapshots at which we are sampling this signal. Now, of course, the faster you sample, the more accurate picture you are going to get of what that analog signal looks like. So if we look at the sampling rate depicted here, we see the dashed line is our digital representation, because what we can do is just approximate and say, okay, from one sample to the next, it must have just continued, and then it either rose or fell to the next data point level. And the faster you sample, the more likely that your digital representation is going to track the actual analog change that occurred from one point to the next. This is showcasing a rather primitive digital representation with a fairly slow analog to digital converter, which is not fully capturing the essence of that analog signal. You get a bit of an idea here of what that signal looks like, but a much faster sampling rate would be needed if we wanted our digital signal to track our analog. So what does an analog to digital converter do? Well, it takes in that sampled voltage and it creates a binary value that is representative of the analog voltage. The binary value is established based upon a minimum and maximum voltage, basically an envelope in which we are going to fit our signal of interest between. And then we have a certain number of bits available. So the more bits we have available, the better resolution we have to distinguish different voltage levels. So this illustrates a simple 3-bit analog to digital conversion. Effectively, what we can do with 3 bits is we have 8 different binary values that are possible, and we are sorting our voltages into 8 different bins. And so if the voltage measured on the total range from 0 to 10 volts, if the voltage measured is somewhere between 0 and 1.25 volts, we'll assign the lowest possible bin, or bin 0 being 0, 0, 0. If we are somewhere between 1.25 and 2.5, we'll be in bin 1, which is 001, and this will continue all the way up through bin 7, which represents 111. With 3 bits, we can sort our voltage into 8 different voltage bins. And every time we add another bit of resolution, we're going to double the number of bins that we have that we can sort our analog signal into. 3 is a very small number of bits. Most modern day analog to digital converters will have 8 or more bits. In many cases, higher end ones will have 14 or 16 bits. And we will talk about how the microcontroller we're using in this class uses 10 bits to represent the analog signals that it is digitizing. The way these binary values come out is through what is known as successive approximation. And with successive approximation, what we are using is a bitwise approach to quantifying the analog signal in a digital format. And so in this process, what we do is examine whether or not we are above or below half of the full-scale voltage. Then we can look at the next bit by saying, okay, is the remaining voltage above or below 1/4? And then we keep going all the way through until we get to our last bit, every time each bit representing half as much voltage as the previous bit. So this is an example here. Let's suppose our input signal was represented by the dashed line you see on the screen. The most significant bit on the left is going to represent 1/2 of the full scale, and you see the thick black line indicating where 1/2 of full scale would be. Well, our input signal is actually less than that, and so what we're going to do with the most significant bit is put a 0 if this line is below half of full scale, and we would put a 1 if it was above half of full scale. Since it's below, we put a 0. Then we move on to our next bit, and that next bit represents 1/4 of our full scale voltage. Well, we didn't take anything away from putting a half of full scale here because we were less than that, and we see that our signal here is in fact greater than 1/4 of full scale, and so we are going to put a 1 down here. And what this means is we have now represented 1/4 of full scale within the voltage, and so then what we can do mathematically is before we go on to the next bit, we can ask ourselves, okay, what voltage remains? We've already represented 1/4 of the full scale voltage. How many more volts do we have that we have not yet represented? And that difference is basically the difference between this line and this line right there in terms of voltage. The next bit represents 1/8 of full scale. And so since we already have a 1 here, the question is our line representing the input signal, is that more than 1/4 plus 1/8 of full scale? And it in fact is, so we put a 1 right there. Then we move on to the next bin, which would represent 1/16 of full scale. And we see that we do not meet the threshold for that with our remaining voltage. We've already represented 1/4 plus 1/8. In order to get all the way to 1/4 plus 1/8 plus 1/16, then our signal would have to be above this solid black line, and it's just slightly below, so we would put a 0 there. And this process will continue all the way through until we get through all of the bits that we have. So now let's talk about how analog to digital conversion is performed on the PIC16F1719 microcontroller. We have 28 different input channels available for us to connect analog signals to and to process them on this particular PIC. The digital representation comes back in the form of a 10-bit binary value, and because we have an 8-bit architecture, that means those 10 bits need to be spread across 2 different registers, and we will use ADRESH and ADRESL to represent the higher bits and the lower bits respectively. Depending upon how you configure it, you can have these bits be left justified, meaning the most significant 8 bits end up in ADRESH and the least significant 2 end up in ADRESL, or you can be right justified, meaning that the least significant 8 bits end up in ADRESL and only the most significant 2 bits end up in ADRESH. And this is a bit that we will configure. We'll talk about that in just a moment. In this case, the reference voltages are either VDD, which is plus 5 volts, and ground, or we can also have user configurable analog voltage references. Now, in the remainder of this course, we will only use the plus 5 volts and ground as our reference voltage. Even though we can use a specific voltage range, we will not choose to do that. If you look at Table 1-3 on page 19 of the datasheet, it tells you about each of the pins on the microcontroller that we are using and the various functions that each of those pins can obtain. We've spoken quite a bit about each of the ports and how we can use them as analog or digital and inputs or outputs in this class. We have yet to talk about which pins can be used in the analog mode. And it turns out we have a 40-pin microcontroller. Some of those pins cannot be used for analog input. For example, there are some pins that are associated with the power and the ground. We also have a pin that is associated with the master clear. That cannot be used for an analog input. We have 2 pins that are associated with the oscillator crystal. They cannot be used for an analog input. But most all of the other channels that are available, the other pins, can be used as analog input. And here you see a mapping of which bits in port A on the far left, port B, port C, port D, and finally port E map to the various analog pins. Analog pins are numbered AN0 through AN27. And you will also note that in some cases the analog numbers are in the order of the pin numbers for the digital representation on that signal or on that particular pin. For example, AN0 is the same as RA0, AN1, RA1, AN2, RA2, AN3, RA3. Note there is not an analog signal on the same pin as RA4, but AN4 is on RA5. And then we see with port B, these are kind of jumbled around a little bit. So RB0 is AN12, then 1, AN10, 2 and 3, 8 and 9. And so we see that it jumps around a little bit. But we have analog pins on all of our ports from A through E. And so you can see that there is no shortage of pins available for analog configuration. Table 21-3 in the datasheet summarizes all of the registers that are associated with the analog to digital conversion module. This may appear to be quite a bit, but we will go ahead and walk through some of these, and you will see that it is not nearly as complicated as it may seem. The first registers we need to be aware of, we've already talked about in this course, largely because we had to clear them to make them into digital mode, and that is our AND-cell registers. We have AND-cell A, AND-cell B, all the way up through AND-cell E, and that is short for analog selection. That allows us to select certain bits to be in the analog mode or the digital mode as needed. The analog mode consumes higher power, and so unless we really need an analog input, we should convert things to digital. The problem is that the default setting is for these things to be analog, and so if we want to use things as digital, as we've done throughout the rest of the course, and we want to save energy, we need to override that default value of 1 and put in specific values of 0. So we should only put in 1s in the corresponding AND-cell registers associated with where we want an analog input. So for example, if you wanted an analog input on RA2, that would correspond to ANSA2 right here, because this corresponds to RA0, RA1, RA2, RA3, RA5. And so remember, putting a 1 makes things analog, putting a 0 makes things digital. The grayed out boxes are the pins that are not available for analog mode. So for example, up here, RA6 and RA7 are not available for analog mode. because that is where the crystal oscillator signal comes in. Down here, RE3 is not available for analog mode because that is where the master clear is set up. That's where our reset switch is connected. And then additionally, we have 2 pins in port C and 2 pins in port B that are not available for analog mode. The ADCON 0 register is used for several purposes. It is used to configure the analog to digital conversion, largely by choosing which channel are we going to convert, and then it is also used to power on or turn off the analog to digital conversion module, and it is used to initiate the analog to digital conversion by saying go and sample a particular analog signal. So bit 7 of this register is not implemented. It'll read back as a 0, so you don't need to worry about that bit. The next 5 bits are used to determine which channel you are pulling in analog from. So it is important to note that with our microcontroller, even though we have 28 different analog inputs, we will cycle through and only be able to digitize a single analog input at one time. Now we can do this very quickly. So if you are sampling multiple sensor inputs, as we will later in the course when we get into interfacing with a 3-axis accelerometer, what you will have to do is collect data from one channel and then reset the channel that you're collecting data from, capture that channel, convert it into digital format, capture that data, and then convert to the other channel and go on until you have captured all of the channels. So the PIC does not natively support doing an analog to digital conversion of multiple pins at the exact same time, but the good news is it is very quick and allows us to collect from as many analog pins as we need to. So here you see the 5 bits that you put in for choosing which channel that you want, and then the bit 0 is perhaps the most important bit for the analog to digital conversion module, because without setting this, the entire analog to digital conversion module is powered down, which is good if you're not needing analog signals to be coming in through an analog to digital converter. But if you are needing that, it is very important that one of the first things you do is power on the ADC module. It is also important that you use this go bit when you have everything set up and are ready to go ahead and initiate the analog to digital conversion. We will talk about later, you don't want to do it all in one fell swoop. You will want to set up the channel first, and then once all of that is set up, then you will initiate the analog to digital conversion. ADCON 1 is another register that allows us to configure the analog to digital conversion input. The most significant bit here is ADFM, and that is what determines whether the data that is coming back from the conversion is going to be right justified or left justified in the data registers, the analog to digital result registers. This register here, also on the next 3 bits, the ADCS, determines how quickly you are going to sample. Now, previously I had said the faster you sample, the more accurate you're going to have of a picture of what's going on in an analog signal, and that is very true. But it's important to take into consideration how quickly you really need to sample based upon how likely that signal is to change abruptly. So for example, if you're tracking the temperature outside during the day, you perhaps don't need to track that 1,000,000 times per second. But if you're trying to track a signal coming across an internet stream, or you're trying to track some kind of a biosignal that may be oscillating at a very high frequency, you may want to sample that at a much higher rate. Now there are some trade-offs. The faster you sample, the more power you are going to consume in your microcontroller. However, the faster you sample, the better your digital representation is going to be for the analog signal. Also keep in mind, if you are trying to store these things out to file, the faster you sample, the larger those files are going to be. So it's important to keep in mind that faster sampling should only be done if it helps to improve the representation that we get of the analog signal in the digital domain. The next bit is unimplemented, bit 3, and then our last 3 bits are used to choose what our high and low voltage references are. And in this case, we're always going to be using our plus 5 volts and our ground. So our ground is VSS. That is what I've highlighted there. You should always put a 0 for bit 2. And then we are going to use VDD. That is our plus 5 volt signal for our positive analog to digital conversion. Why would you ever want to choose something different? Well, if you know that a signal range is always within a certain window that may be not always going all the way up to 5 or all the way down to ground, you can choose to generate an external analog signal and have that be the boundary. But we are not going to do that this semester. I just want you to be aware that is a possibility. This graphic depicts how the analog to digital conversion results are stored. So ADRESH and ADRESL are our analog to digital result registers. H stores the high byte and L stores the low byte. And so if you choose for your data to be write justified, what you will have are 6 zeros to the left in ADRESH, your most significant 2 bits in the least significant 2 bits of ADRESH, and then your least significant 8 bits stored down in ADRESL. If you choose to be left justified, the opposite is true. Those zeros get padded at the end of ADRESL, and your data, the most significant 8 bits, end up in ADRESH, and the least significant 2 bits end up as the most significant 2 bits of ADRESL. And this is all chosen by that ADFM, which is, as we mentioned here, in the ADCON1 register. That is our most significant bit in the ADCON1 register. ADCON2 allows for the analog to digital conversion to be automatically triggered based on events. So for example, you can automatically trigger an analog to digital conversion based upon an overflow of some of the timers. We will actually not be using this register in this course, and we're going to accept the default value of 0, which effectively turns off this automatic triggering of an analog to digital conversion. The tris registers are also very important, so anything that you want to make an analog input, you should make an input in the corresponding tris register. And to make things input, you should make them a 1. So you should have already seen that in the digital world. The same is going to be true if you're talking about an analog input. We should put a 1 in the corresponding bits of the tris register. So for example, if we wanted to do an analog input on the same pin that is also lived in by port A pin 0, then what we need to do is put a 1 in our tris A0, making that particular bit indicate that we are doing an input on that pin. We can also establish an interrupt for when the analog to digital conversion is completed. This is a personal preference. In many cases, you may want to use an interrupt so that things are handled in the background. Once the analog to digital conversion is finished, you can use the interrupt service routine and you can handle that. Otherwise, what you have to do is continue to poll the bits and see when things have occurred, when the conversion has finished. And so regardless of whether you use the interrupt or not, the ADIF flag will be set to indicate that the analog to digital conversion is finished. Also, the go bit that you will set to start the analog to digital conversion routine will be cleared once the analog to digital conversion is finished. So here are the basic steps to perform an analog to digital conversion using the PIC16F1719. First of all, configure your ports for analog in the AND cell registers and configure them as inputs in the tris registers. You also want to make sure that the default in bit 7 of the option register is set to a 1. And this just disables some weak pull-ups which may cause false analog signals on some of your pins. Then we want to set up in ADCON1 whether or not we want our results to be left or right justified. We want to select a sampling rate, and then we want to establish the reference voltages, which throughout the rest of this course will be plus 5 volts and ground. We also want to use ADCON 0 first of all to power on the analog to digital conversion module and to choose the particular channel that we wish to sample. But we don't want in the same instruction to also set the go bit. We will put in the powering on of the A to D and the channel with the go bit cleared, and then once all of our other settings are in there, we can set the go bit to say go and perform this analog to digital conversion. Then we're going to check our ADCON 0 to wait until the conversion is done. We can poll on our go bit. We can also poll in our peripheral interrupt register to see if we have that flag set. Or we can use an analog to digital conversion interrupt, which is a peripheral interrupt, and that can handle it. Then, once we're completed, we can read our values back in ADRESL and ADRESH and process the incoming data.